Hello everyone. Now we will discuss on some numerical problems based on our last 4 classes. So, the first problem, the statement is find out the DO in aerated water at 25 degree centigrade in a treatment plant. Kh of O2 at 25 degree centigrade is 1.26 into 10 to the power minus 3 m per atmosphere. So, Kh is the Henry's constant and molecular weight of oxygen is 32 gram per liter. So, it is given. So, we have to find out the DO in aerated water. As you know that in any river stream or in aerated water, so oxygen present in air and oxygen present in water. So, these are in equilibrium, and what will be the equilibrium concentration of oxygen in water phase, that is defined by this formula, that is Kh is equal to concentration of oxygen in aqueous phase divided by partial pressure of oxygen in the atmosphere or in the air, where the water is in contact with the air. So, this Kh is nothing but Henry's constant. So, this value is given here 1.26 into 10 to the minus 3 mole per atmospheric pressure. Therefore, we need to calculate oxygen concentration. So, Kh into partial pressure of oxygen. So, we have to get this formula, aqueous concentration of oxygen is equal to Kh into partial pressure of oxygen. Now, what is the partial pressure of oxygen? If it is 1 atmospheric pressure, then partial pressure we can calculate on the basis of volume fractions if we know. So, as we know for air, the 21% is for oxygen and around 79% is for nitrogen. If we ignore the other impurities, almost this is that we know. So, on that basis we can calculate that partial pressure of oxygen is nothing but 0.21 atmosphere, when the total pressure is 1 atmospheric pressure. So, Kh value we will put it here 1.26 into 10 to the minus 3 mole per atmosphere into 0.21 atmosphere. So, it will atmosphere will cancel. So, we are getting here 0.0002646 m. So, then the 1 mole of oxygen is equal to 32 gram. So, we will multiply it here 32. So, it is a gram. So, if we want to convert it into mg, we will again multiply by 10 to the power 3. So, this into 32 into 10 to the power 3, that is equal to 8.467 mg per liter. So, this is the concentration of the oxygen in the water. So, now the problem 1 is solved. Now, we are coming to problem number 2. So, the statement is acetic acid, that is CH3COH or vinegar, is oxidized to carbon dioxide and water by microbial action. A vinegar manufacturing plant has 50 mg per liter of acetic acid in its effluent wastewater. The plant flow is 500 meter cube per day. How much oxygen is required each day to oxidize the vinegar? So, that we have to calculate. So, we will be writing the stoichiometric equations, and then we will get the mass balance and balance the equation, then we will find out what is the oxygen requirement for the degradation of it. So, first the equation must be balanced. These equations, that is acetic acid will react with oxygen and it will give us carbon dioxide and H2O. So, if we get the balance, so 2 moles of oxygen is required to react with 1 mole of acetic acid to give 2 moles of CO2 and 2 moles of H2O. So, in this case 2 moles of oxygen are required to oxidize the acetic acid to carbon dioxide and water, that I have discussed. So, the amount, thus the amount of acetic acid to oxidize each day, what will be, that we have 50 mg per liter of acetic acid, we have 50 mg per liter of acetic acid, and then we will convert it into gram. So, divide it by 1000 and we have 500 meter cube per day effluent generation capacity. So, multiply it and then this is 1 meter cube is equal to 1000 liter. So, we will multiply it here 1000 again and then 1 mole acetic acid divided by 60 gram, because we are converting it into mole. So, acetic acid you see CH3 COOH. So, it is coming 12 plus 3 plus 12 plus 2 into 16 plus 1. So, we are getting 12 plus 3 plus 12 plus 32 plus 1. So, that is equal to 60. So, that molecular weight of acetic acid is 60 gram. So, then by this expression we are getting acetic acid concentration will be this much, this mole per day. So, now since 2 moles of oxygen are required for each mole of acetic acid as per our previous expression, the required oxygen is equal to how much? How many moles of acetic acid we are having? We will be multiplying it with by 2 mole oxygen. So, that is equal to 834 mole oxygen per day, because the MHAC was 417 mole per day. So, now oxygen which will be required, that is 834 mole per day. So, then what will be the mass of this oxygen? We will be multiplied it with the molecular weight of oxygen, that is 32 gram per mole. So, that is 32 gram oxygen. So, that is equal to becoming to 26,700 gram oxygen per day, that is equal to 26.7 kg oxygen per day. Now, the problem number 2 is solved. Now, we will see the problem number 3. The statement is, if 500 mg per liter ethanol, a biodegradable compound, is completely oxidized, calculate theoretical oxygen demand, chemical oxygen demand, ultimate biochemical oxygen demand, BOD 5 and total organic carbon if Kd is equal to 0.023 per day. Okay. So, we have to calculate all those things, that is THOD, COD and ultimate BOD, BOD 5 and TOC. So, now we will see the conversion, the equation, that is C2H6O ethanol, C2H5OH plus 3O2, it is giving us 2CO2 plus 3H2. So, this is the stoichiometric expression. So, theoretical oxygen demand, we can assume that 100% conversions of this ethanol is possible by the oxygen. So, then what will be 1 mole ethanol requires 3 mole oxygen. So, 3 into 32 gram of oxygen per 46 gram of C2H6OH, that is C2H5OH, C2H5OH. So, this is molecular weight nothing but 46. So, this 46 gram of C2H5OH and then that is equal to, by this expression, by solving this we can get 2.09 gram of oxygen per gram of C2H6O. So, that is equal to, we can write 2.09 mg of oxygen per mg of C2H6O, because this is gram per gram. So, mg per gram, mg per mg, that will be same. Now, what is given, that 500 mg per liter ethanol concentration. So, 2.09 into 500 mg per liter, that will be the oxygen requirement. So, we will multiply it here, we multiply 2.09 with this 500 and get 1045 mg per liter or ppm. So, that is the oxygen requirement theoretically. So, that is theoretical oxygen demand. Now, COD is equal to BOD ultimate, that is equal to theoretical oxygen demand. Okay. So, COD will be same and ultimate BOD will be this one and theoretical oxygen demand also this one in this case, and then BOD 5 we have to calculate. See, if we want to calculate the BOD 5, we have one formula that BOD 5 at any time T is equal to ultimate BOD into 1 minus e to the power minus k into T. So, that is equal to LU into 1 minus e to the power minus k T that we have discussed in our previous class, or we will discuss later also. So, here BOD 5. So, in this case T equal to 5, T equal to 5, when we will be taking the BOD 5, then it will be T equal to 5, and this k is nothing but this value is given. So, LU we are getting here. So, we will be putting this value, that is equal to 2.09 gram oxygen per gram of C2H6O. So, we multiply this with this 1 minus e to the power minus k T this function. So, e to the power minus 0.023 into 5. So, that we are getting 0.23 gram of oxygen per gram of C2H6O, or that is equal to how much we can write. So, if it is this gram of this, that means 0.23 into 500, that will be our ppm as mentioned here, and the similar way we can get the value as this ppm of BOD 5. And what is total organic carbon, TOC, total organic carbon? So, here organic carbon present here 2 into 12, that is equal to 24 out of 46 gram. So, that way we will be calculating the theoretical oxygen demand. Total organic carbon is 2 into 12 divided by 46 gram of TOC per gram of C2H6O. So, that is we are getting equal to 0.52 gram of TOC per gram of C2H6O, and that is equal to 0.52 into 500, because we have 500 mg per liter. So, that is equal to 260 ppm. So, now we are able to calculate all the values as asked in the problem statement. Now, we will move to problem number 4. The statement is the reported chemical concentration of a mineral water is sodium plus 0.65 mg per liter, potassium plus 0.4 mg per liter, Mg2 plus 19 mg per liter, Ca2 plus 35 mg per liter, Cl minus 0.8 mg per liter, SO4 2 minus, that is 14.3 mg per liter. So, HCO3 minus, so this will be superscript, here all are these 2 minus superscript. So, that is equal to 189 mg per liter, NO3 minus, that is equal to 3.8 mg per liter. The pH of the water is 7.3. Then what is the hardness of the water in mg per liter calcium carbonate? We have to calculate. We also have to calculate, we also have to see is the chemical analysis correct. Okay. So, what we will do? We will see the error in the ion balance. So, ion balance error is necessary to be calculated. So, in this case calcium plus 2 plus, calcium 2 plus is equal to 35 mg per liter. We will be converting it into mg per liter form. So, at first we will be 35 mg per liter, and then we will divide it by the equivalent weight of it. What is the equivalent of calcium? That is equal to 40 is the molecular weight and divided by 2 valency. So, that is equal to 20. So, then this one 35 divided by this 20 multiplied by the equivalent weight of this calcium carbonate. So, then that is equal to nothing but 100 by 2, molecular weight of calcium carbonate 100. So, divided by 2 is equal to 50, that is the equivalent weight of calcium carbonate. So, that way we are getting calcium 2 plus is equal to this into this divided by this, that is equal to 87.5 mg per liter as calcium carbonate. The similar type of calculation we have already done in our previous classes. So, similarly for magnesium 2 plus we have 19 mg per liter. So, divide it by this, in this case of magnesium 24 molecular weight by 2. So, that is your equivalent weight. So, that is, and that equivalent concentration will be converting it in terms of calcium carbonate. So, we have to multiply it with the equivalent weight of the calcium carbonate. So, that is 100 divided by 2. So, then we are getting 79.2 mg per liter as calcium carbonate, and total hardness then calcium plus calcium 2 plus and magnesium 2 plus. So, here we are having 87.5 plus 79.2, that is equal to this one, this is not. So, 166.7. So, 87.5 divided by 79.2. So, 166.7. Okay, this is not. So, convert the concentration of the major cations and anions to equivalents per liter, then sum of the cations and anions to see if there are within 5%. That means, we are going to calculate the error in the ion balance. So, sum of cations milliequivalent if we calculate, and then we can get the difference, then we will get the ratio difference by sum into 100. So, that will be the error. So, we are having here Ca2 is 35, Ca2 plus is 35 mg per liter. So, that we can divide it by 1000. So, it will be gram per liter, then multiply it with this 2 equivalent per 40 gram. So, that is equal to 1.7 into 10 to the minus 3 equivalent per liter. Similarly, for magnesium 1.6 into 10 to the minus 3 equivalent per liter, and potassium is also 1 into 10 to the minus 5 equivalent per liter, and Na plus is 2.8 into 10 to the minus 5 equivalent per liter, and sum of the cations equals to, if we sum up all those 4 cations, then we will get 3.338 into 10 to the minus 3 equivalent per liter. And then in case of anions, so we have HCO3 equal to how much? 139 mg per liter. So, we can convert it, we can get it from 3.1 into 10 to the minus 3. How? Because we have to divide it 189 divided by 61, the equivalent rate of HCO3. So, that we are, it is coming 3.1 into 10 to the minus 3 equivalent per liter. Already similar calculations we have done in our previous class. So, detailed calculation is not shown here. So, similarly chloride we can get 2 into 10 to the minus 5 equivalent per liter, and SO4 2 minus, this is equal to this one, and NO3 minus is equal to this one. So, sum of these anions we get by summing up. So, 3.481 into 10 to the minus 3 equivalent per liter. So, what is the error? So, this minus this divided by this plus this. Okay, so, error, if we take error is equal to, say, cation is this one, anion is this one. Okay, so, what is the percentage of error with respect to this? This is the percentage, and if we take this 3.338 minus 3.48 divided by 3.338 plus 3.481. So, because the sum of all cations and anions are within 5% of each other, we can assume that the analysis is correct. Now, we are coming to problem number 5. The statement is, the average airborne concentration of chloroform was found to be 0.4 microgram per cubic meter at 293 K and 1 atmospheric pressure, and the mean concentration of chloroform in water was estimated to be 42 microgram per liter. A typical adult inhales 20 cubic meter of air and ingests about 2 liter of water per day. Compare the exposure via inhalation with the exposure via ingestion. So, now we will see, let us take a basis. What is this? The air consumption per day is equal to 20 cubic meter or meter cube. Water consumption is 2 liter. So, chloroform present in 20 meter cube air is equal to 20 into 0.4 microgram. So, that is equal to 8 microgram. Chloroform present in 2 liter of water is 42 into 2 84 microgram. Thus, intake of chloroform per day through water, that is 84, is more than the intake through air. Problem number 6. Statement is concentration of thorium in monazite sand is 0.04 microgram per liter. How much thorium is present in 100 kg of sand? Bulk density of sand is 1650 kg per meter cube. So, our basis is 100 kg sand. So, what is the volume? 100 kg and it is given this kg per meter cube. So, 1650 kg per meter cube. So, if we want to convert it in terms of liter basically volume. So, we have to convert this meter cube to liter. So, that is 1000 relationship. So, that 1000 is coming at the numerator. So, 100 kg into 1000 L per meter cube by 1650 kg per meter cube. So, that is equal to 60.61 liter. Now, amount of thorium in 100 gram in 100 kg sand, that is equal to 0.40 per liter into this much of liter we are having volume. So, we will be multiplying it with 60.61 liter. So, that is equal to 2.42 microgram. Now, we are coming to problem number 7. So, the statement is mole fraction of aqueous glucose solution is 0.025. What is the molar and mass concentration of glucose? Assumption density of the solution is 1. So, now as per the statement, for every 0.25 moles of glucose there are 0.975 moles of water, because the solution is glucose and water. So, 1 minus 0.025, that is equal to 0.975 moles of water. So, 0.025 moles of glucose for 0.975 into 18 gram of water, because molecular weight of water is equal to 18. So, that is equal to 17.55 gram, or we can consider that 17.55 ml of water, because their density is 1 gram per cc. Now, 0.025 divided by 17.55 into 1000 moles of glucose in 1 liter of water. So, that is equal to 1.42 moles glucose per 1 liter, that is equal to 1.42. So, the solution strength is 1.42 molar. So, molecular weight of glucose is equal to, you can calculate here C6H12O6. So, it is coming equal to 180. So, we will be what we will do, we can multiply it 180 into 1.42. So, we will be getting 256 gram per liter. Alternatively, the mass concentration you can calculate 180 into 0.025 divided by 17.55 into 1000, the formula which we have used here. So, that we can get 256 gram per liter. So, now we are able to find out the molar concentration and mass concentration of glucose in water. Now, problem number 8. The statement is 10 gram of table salt, that is NaCl, in pure water is dissolved to make 1 liter of solution. Determine for Na plus the mass fraction, percentage ppm, mass concentration, molarity, normality, mole fractions in the solution. So, molecular weight of NaCl is equal to, we know, 23 for sodium and then 35.5 for chloride. So, that is 58.5, and then 10 gram NaCl, how much? 10 divided by 58.5, that is equal to 0.17 mole NaCl. So, Na plus is equal to 0.17 mole into 23 gram per mole. So, that is equal to 3.91 gram of sodium plus. So, mass fraction in salt equal to how much? So, 3.91 into 100 divided by 1000. Why? Because 3.91 gram is sodium and the total is say 1 kg. So, 1000 gram if we consider the density 1. So, this 3.91 by 1000 into 100. So, this is the mass fractions in salt. So, we are getting equal to 0.39%, and if we want to convert it into percentage to ppm, we have to multiply it with 10 to the power 4 factor. So, then we are getting 3900 ppm. Then mass concentration, if we want to calculate, then 3.9 gram per liter, that is equal to 3900 mg per liter in aqueous system, we can get it. And then molarity, molarity is 0.17 mole per liter or 0.17 molar, and normality is 0.17 equivalent per liter, that is equal to 0.17 n normal, because it has valence equal to 1. So, mole fraction, now if we want to get the mole fraction, so how many moles of sodium is there and how many total moles are there, that is water plus sodium. So, 0.17 moles we have got for it, and another will be for mole will be for water. So, we have 10 gram. So, 1000 minus 990, that will be for water mass divided by 18. So, that will be number of moles of water. So, this plus this mole of water total mole, and so this mole by total mole is equal to mole fraction. So, we are getting 3.08 into 10 to the power minus 3. So, as per the problem statement, we are able to solve it. Now, we are coming to problem number 9. So, the statement is a water sample is known to contain calcium, sodium chloride and bicarbonate. The result of an analysis were as follows: calcium 60 mg per liter, sodium 46 mg per liter, chloride 71 mg per liter. Molecular weight calcium we know that 40, sodium 23, chloride 35.5, bicarbonate 61. Calculate concentration of bicarbonates, percentage sodium and RSC. Also comment on suitability of this water for irrigation applications. So, this is our problem statement, we have to solve it. So, what we will do? At first we will do the estimation of the concentration of bicarbonate, the first question. So, here we have to calculate the concentration in milliequivalent per liter. So, we are calculating for calcium 2 plus, that is we have 60 mg per liter. So, 60 divided by this equivalent rate, that is 3 milliequivalent per liter, because the concentration is mg. So, milliequivalent per liter. Similarly, for sodium plus we are having 46 mg. So, divided by 23, that is the equivalent rate of it. So, 2 milliequivalent per liter. For chloride we are having 71 mg per liter. So, divided by 35.5, that is almost 2, but it is not given how much bicarbonate is available, but we have to calculate from the ion balance. So, sum of cations we are getting this 3 plus 2, that is 5 milliequivalent per liter, and if there is no error in the ion balance, if we assume, then we can assume that the sum of the anions will also be 5 milliequivalent per liter. So, in that case bicarbonate concentration will be the total anion concentration minus the concentration of chloride. So, that is total is equal to 5 and minus chloride is equal to 2. So, 5 minus 2, that is equal to 3 milliequivalent per liter, or 3 into 61, that is your molecular weight equivalent weight. So, that is equal to 183 mg per liter. So, that is the concentration of bicarbonate, and then you have to calculate percentage sodium and RSC. So, for the calculation of percentage sodium, the formula is sodium concentration divided by sum of the concentration of sodium plus potassium plus calcium plus magnesium into 100. So, in this case we have calcium and sodium, no potassium, no magnesium. So, we are having these will be 0. So, calcium we have, potassium and magnesium 0. So, we are having 2 for sodium and 3 for calcium and 2 for sodium. So, that 2 by 3 plus 2 into 100. So, that is equal to 40. So, that 40% sodium is there. And for the second RSC, RSC is equal to how much? This is the formula, CO3 plus ACO3 minus Ca2 plus Mg2 plus. So, now in this case Mg is not present, so 0, CO3 is not present, 0. So, bicarbonate is 3 and carbonate and calcium 2 is also 3 milliequivalent per liter. So, 3 minus 3 equal to 0. So, we are able to solve the second part, and in the last part of this problem it was asked to comment on the suitability of the water for applications in irrigation. So, we know that there are two criteria, one is a percentage sodium or RSC. So, if percentage sodium value is less than 60 or RSC value less than 1.25 milliequivalent per liter, then the water is suitable for applications in irrigation. So, in this case these values are 40% and 0. So, this is satisfying the conditions for both percentage sodium and RSC values. So, therefore, the water is safe for the irrigation. Now, the problem is solved. So, up to this in this class, thank you very much for your patience.